In the next subsection, I want to discuss how to compute the suffix array of a string in linear time. We've seen a simple n log n method using the fat pivot radix quicksort, which is actually very easy to implement and gets the job done in a reasonable time. But the theoretically best possible is linear time, and for that we have to work a little harder. Before we can describe this algorithm that gets the suffix array computed in linear time, I need to introduce the inverse suffix array, because it turns out the algorithm is easier to understand when we compute the inverse suffix array, and then can go back and forth between that and the suffix array itself. Conceptually, the inverse suffix array, this array R, is a very simple thing. It just says, find me the inverse permutation that is encoded by the leaf array. Something I haven't stressed before, the suffix array is actually a permutation. So it stores the numbers 0 up to n in an array of size, in an array of 0 up to n. And it stores every number exactly once, so it just permutes these numbers in some way. And every permutation is invertible. There's an inverse permutation, and that one's stored in R. That's one way of expressing this. The other way of saying it, whenever we have that the rth leaf in the left to right order, the rth leaf in sorted order starts at position I in the text, then R of I is little r. And another way of saying this is that the suffix starting at position I has rank R, because there's R suffixes that are smaller than it in lexicographic order. So that's why I chose R for the inverse suffix array, because it's reminiscent of rank. And that's what it is. It stores the rank for the suffix starting at a position, whereas L stores the leaf in the left to right order, so where the suffix started. It's also, if you want, the left index of the suffix. And this picture below is, I think, a good way to memorize these two notions and to keep them separate, because I personally tended to mix those up easily, so this is also for myself. If we have a text banana bin, we write all the suffixes in text order, where we just move the next character, so you have this nice triangle shape. If you have this here, then I is just the numbers 0 up to 9. That's the starting position of the suffix. And then R of I tells you the rank of this suffix in the sorted order, lexicographic order. So the first one is actually always the one that's just the dollar by definition. But then the next one, who comes first, that's depends on the text, and in this case it's the suffix starting at position 5. On the right, I have the same suffixes, but now sorted lexicographically, whereas here things are in text order, how they appear in the text. And having the suffixes in sorted order means that the rank goes from 0 up to 9 in just counting up. And then the suffix array tells you where's the starting position of that suffix. So the smallest suffix in the text starts at position 9, it's just the dollar, and so on and so forth. And you see it occasionally happens that those two numbers match, but in general they don't. The second smallest suffix starts at position 7, for example. So those are the two things to keep in mind. Keep in mind this picture, the triangle on the left, the jagged sorted list on the right. And then L and R have another nice meaning that luckily coincides. L means you are on the right and you want to go to the left. So it tells you where to find a certain string in the left picture. if you have the string here, naban, it's the 8th in the sorted order, and then the L entry tells you that at position 4 you find the same string on the left. And same R, which I took standing for rank, can also mean right. If you have a string here, maybe the whole text, it starts at position 0, so that's this one here. If you look at R of 0, it tells you that's the 6th smallest, so it appears at position 6 on the right. Okay? I hope that these mnemonics stick in your mind and avoid you mixing up the two notions, the two concepts. Okay, if that is clear, then let's move on to the linear time algorithm for constructing suffix arrays. There's different algorithms that do this. What I will present is called the DC3, difference cover 3, or the skew algorithm. The name is a bit weird, but that's what got stuck. I don't want to explain where this comes from, really. That's just in case you're an expert and you see other algorithms. This is the one we will talk about. It proceeds in 3 curious steps. The first step is we make a recursive call and we compute the rank array, so the inverse suffix array, for some of the suffixes, but not all. Well, that wouldn't work. We leave out all the suffixes that start at a multiple of 3. So we recurse on 2/3 of the size, right, by leaving out every third. And obtain the sorted order. So R, again, the rank array, tells you, if you're given the starting position in the text, it tells you how many suffixes are smaller than this. Okay, that's the first step. How long that takes will depend on the other algorithm because it's recursive. We will see that eventually it is linear time, but that only follows at the end. The second step is, given that we know these ranks, we induce the ranks for the remaining suffixes. Now, in both cases, because we recursively call here, these ranks are only internally. They only rank how the suffixes are sorted within each other. And the same thing here, we essentially sort the list of suffixes, but only those that start at multiples of 3. And to speed up this sorting process, we use the information from R12. And finally, we have 2 sorted lists, so we merge them together, like in merge sort. And that will produce the rank array for the entire input. R, again, the rank array is the inverse suffix array, so if you have that, you can easily translate it to the suffix array. So that will construct L as well for us. Okay, now the magic here comes in showing that step 2 and 3 both run in linear time. Step 3, you might believe that this is doable because merging is usually running in linear time, but there's a caveat here because we're merging strings, and merging needs pairwise comparisons. So again, we have to speed up comparisons here in this third step for that to run in linear time. And for the second step, we're sorting. These are still n/3 suffixes roughly, right? So if we were to sort them with any simple means, it would take n log n time. We have to do it in linear time. So we have to use this information that we've computed recursively for that. And that will be the main trick of this algorithm. But let's first suppose we have already convinced ourselves that this is the case. What is the total complexity then for the recursive calls? Well, this is the step 2 and 3 on the top level. So we spend linear time here, linear time here. Let's just renormalize that so that the constant is 1. That's the top level. We make a recursive call, and now on this next level, we only have 2/3 of the strings. We will have another step 2 and 3, and they take together, they take 2/3 n. But that second step also has a recursive call, and it takes 2/3 of 2/3, and so on and so on. So you see, what we get here is this geometric sum. In every step, we get rid of a constant fraction of the input. So that means after we factor out n, we have this geometric series, and that is bounded by a constant, in this times 3. So that shows that the total cost is linear in n as well. Okay, so that is if the steps 2 and 3 take linear time, the entire algorithm takes linear time. That is a simple application of solving recurrences like you've practiced it in Unit 1. Also in the tutorials, or Unit 0, whatever it was. That proves that the entire algorithm is linear, but we have to show that these 2 steps can be implemented in linear time. Okay, that's just the remark. This algorithm actually computes R, but we can use it to compute L, and we can go back and forth between those. That's always doable in linear time. For the rest of today, I want to discuss this second step. So we assume we have, remember, the recursive call computes, sorts the suffixes, computes the ranks for the suffixes that don't start at a multiple of 3. And we would like to use that information to compute the other ranks. Okay. A little more formally, what I assume here, just to make the notation nicer, is that this array R12 contains the rank of the suffix starting at I among those ranks that are not multiples of 3. If I is such a not multiple of 3, and for the other ones, we just never access this. So what that says is just we spread out the array so that it doesn't use the indices at positions that are multiples of 3. That just makes the notation convenient. Now, our task is to sort this list of suffixes in linear time, and that looks like the same problem we originally started with. So it looks just as hard as the original problem. But here's the trick. Suppose we compare the 2 suffixes T0 and T3. These are very long strings. We don't have the time to compare them character by character. But what we can do is compare the first character, just one. And after we stripped off the first character in T0, there's some character and then a long remainder, but that remainder is just T1, the suffix starting at position 1. And the same thing happens for T3. There's some other character. I don't know if that's the same or not. We don't know in general. Okay, this is should be shorter. So that's T4 because we split off the first character. Now T1 and T4, 1 and 4 are not multiples of 3. So we can take their ranks from what we've previously computed and compare them by just comparing the ranks. That's the magic trick. By splitting off one character, we fall back into the set of suffixes that we know how to compare. And we can use that information to compare these other long suffixes that we didn't know anything about up to that point. So to summarize this, T0 comes before T3 in lexicographic order if and only if this pair as a small string if you want, with the first character of T0 and then the rank of T1. Comes before the pair where we take the third character of the first character of T3 and then the rank of the remainder. Okay. That's the main magic step, and that allows us to induce the ranks in constant time per comparison. So let's briefly look at how we do this in an example. Because there's one step that's still missing. We would still, I've shown you how we can do a single comparison in constant time, but we still have to sort. And doesn't sorting always take n log n time? Well, remember what we discussed when we were talking about the lower bound for sorting. It only needs n log n time if we don't know anything about the objects that we're sorting. And in particular, for small integers, we can sort in linear time. And this is where we'll come back here. We will use that as a black box here, but you actually know how it works. It's just counting sort. But let me finish with this overall picture here first. So this is the list of suffixes that we now have. And we want to sort them lexicographically. We recursively found for all the other suffixes, those that don't start at a multiple of 3, we found the sorted order. And in particular, we know this R12, the rank array. Okay. Now, what we do is, suppose we take this T15. We will transform this string, which is too long to sort efficiently, into something short that we do know how to sort efficiently. And the way to do that is split off the first character, that is just copied down. And then for the rest, S-man turns out to be, well, from T15 we go to T16. So we find that in this list. And in particular, we can look up the rank of this. So T16 is here. And on the other side, if we go to 16, we know its rank is 14. So what we put in here is a 14 as the second component of this pair. And we do that for all the suffixes that start at multiples of 3. And then we use radix sort to sort these in linear time, because they now consist of one character. That's even, if the alphabet is bounded, it's even a constant size. So this is very easy to sort. And the second component is a number that's bounded by n. And this we already know how to sort using counting sort. So that's this result here. We can sort these pairs in linear time by 2 iterations of counting sort. First sort by the second component and then stably by the first. That's how you would usually do this. And then we get the sorted list of these suffixes that start at a multiple of 3. And from that we can find the rank array. That's the second step of the DC3 algorithm. Given the ranks of the suffixes that don't start at multiples of 3, we could find the ranks of those that start at multiples of 3. One little caveat here is that these are ranks within that set. We still have to merge. We still have to do step 3. And that I will reserve for tomorrow.